as well, there are many options you have, okay? Penetration in a fillet weld. So the fillet size, your throat, with a coated electrode, and then the CO2 process. All right. Carbon dioxide shielded mag weld versus coated electrode welding. I don't like this comparison. When we get in the booth, you'll be able to see it a lot better. Okay. Because this isn't always 100% true. All right. Yes, it can burn hot and has capabilities of burning hotter, but it also can be a really messy and nasty process at the same time. And this is very specific to one mode of transfer, preferably. Okay. Electrode diameter influences the size of weld bead, depth of penetration, speed of welding, and so forth. Oh, let me get back here. Sorry. So to get the max deposition rate at any current density, use the smallest wire possible consistent with acceptable weld profile. So general rule of thumb, this is what they say, and it is true. But remember, you have to match, you have to look at everything. You need to look at what thickness is it? Is this a finished product or is it a rough product? Is there going to be distortion, warpage? Will voltages drop down? How can I do this? So for example, vertical down gas metal arc welding is going to produce less heat, less warpage, much more nice appearance in my opinion than going vertical up. Same wire, same everything, but if just the difference alone is uphill or downhill progression, you know, it kind of totally defines this entire thing in some ways. All right. You're starting to learn the weld profiles going forward. All right. So this is kind of a rule of thumb. However, 0.45 and 1/16 inch wires, usually for thicker material, for sure. I wouldn't call it necessarily medium. Very few machines can run 1/8 inch wire. If you run into this, you're usually working at a very heavy industrial fabrication shop with like 4 or 5 inch thick iron. All right. Usually this is considered heavy gauge, puts a lot of heat into this. 2 or 3 passes run in 1/16 inch, especially in the flux core, also in the gas metal arc though. And your interpass temperature's up there to 500-600 degrees. We're starting to have some issues going forward with that, okay? 0.35 is usually the general standard for most solid wire electrodes. So, electrode extension. This is the area where it's the length of filler wire that extends past the contact tube. So, real quick. So if your shield, if your cup is out here, it does not matter. Your electrode extension is from the contact tip to the burn off. Now, if you're shielding, if your cup is out here, your shielding gas nozzle cup is out here, this is called your stick out. So let's not get them confused. The electrode extension is from contact tube to work. Your stick out is from the end of your nozzle to the workpiece. Okay? This is the area where preheating of the filler wire occurs, also called the stick out. Not 100% true. Okay? There is a difference. And you can find it in other books as well. and you get into weld inspection, you'll see the difference, okay? If it is a stick out, if it is the same distance flush. So don't always go off of that. They can be the difference. Go off what I just explained to you earlier. As the extension length is increased, preheating the wire increases and current reduced, which in turn decreases the amount of penetration into the work. So, real quick, the further we get away, less penetration, we start having problems. The closer we get, that means you're losing, your voltage is there. Real quick, very simple. This is a path of resistance, okay? Anytime we're sending electricity further away, we're losing electricity. Whether it be amps, voltage, whatever. The further we send it, the more we lose or the harder it is to get it there. So if you have it a long ways away, you're going to get less penetration, less heat. You get it in closer, it's going to be hotter. It's also going to have better penetrating values. You're also going to find most wires have a span where they're really good, and it's usually about 3/8 to 1/2 inch away from the weld pool is about where the stability is going to be. Your voltage is going to be the best, your wire speed is going to be in mesh, you're going to have a real nice stable arc, okay? Ooh, excuse me. Stainless steel favors shorter electrode extension because it's higher resistivity. Okay. So again, stainless steel, you're going to want to be about half that distance. Okay. You can read through this on your own. Let's get moving on. I don't know that I've seen a lot of it being called a standoff distance. It's usually called electrode extension or a stick out. I usually set my contact tip in just right behind the surface, so that way I don't get it stuck within the weld pool. Okay. Remember, the other thing that matters as well, not just how far away we are, but if this contact tip if the hole is ovaled out, then we need to make sure that we change that contact tube out. Right there, we're losing a tremendous amount of voltage as well. If it's only contacting with half of the wire, then we might be only getting half of the voltage, or same amount of voltage, but to only half of the material, and it takes more to carry it through it. All right? Especially with gas metal arc welding, clean surface is a huge, is very important. It can be a huge factor in the amount of penetration you get and stability as well. Make sure the middle scale is cleaned off, wire wheel it off, make sure it's clean. You start hitting that middle scale and sometimes it'll take a second for it to get gone and burn through it, all right? Trapping slag or mill scale and inclusions inside. All right. Gun travel angle. Can be compared to the angle of electrode and shielded metal arc welding. Drag technique results in high narrow bead with deeper penetration, 10%, 20% drag angle. As drag angle is reduced, bead height decreases, but your width increases. So, just like anything else, if we pull it down this way, we're helping push it up to where it becomes taller. If we pick it up this way, it becomes like not as tall, but it widens out, okay? It'll spread out the weld plug, all right? So that's on a drag technique. Increased travel speeds, characteristic of a push technique. Now, one place that you're almost always gonna find a push technique is gonna be a vertical up. You'll be pushing, but no matter what you're doing, whether you're dragging it or pushing it, you wanna make sure you're staying at that leading edge of the puddle, okay? But not walking away from the weld pool. I prefer to drag on most things, but going vertical up, I have to push. There's no way. Vertical down, yes. Then I'm dragging it. I can help make a decent weld appearance. I will show you in the shop the technique to do that and where one of my concerns are, and it's usually wrap around the side, tying into the bulk of that material on the one edge. Okay, whether you go to the left or if you do a circular J-hook to the right, it depends on the side that you're tying into. Okay, so let me explain that real quick. So it's kind of very similar to this. I'm going to give you a side profile, okay? So if I have a weld bead that looks very similar to this as I'm welding along, okay? And I'm going to be dragging it and building up in this pattern. Now remember, I want to keep my wire here at the leading edge of the puddle, so that I'm guaranteeing my fusion into the base metal, okay? If my wire's back here, then all I'm really doing is kind of laying on the base metal. If I'm just dragging in the center of the weld bead, so here's my weld bead, and my wire's sitting here, basically I'm not getting good fusion, it's just kind of laying on top of the weld pattern, okay? What I want to do is I want to make sure that I'm out here at the front edge of the puddle, either doing a backward C or the E motion, okay, to make sure that I don't have as sharp of an angle here, but maybe breaking it down a little bit like this, guaranteeing that I'm getting better fusion from here to here, and a nice weld profile as well, okay? So that's why I want to stay on that leading edge of the puddle. So, real quick, we talk about tying into the left or the right hand side of the weld bead, okay? So looking at a weld puddle, it doesn't even have to be that, but a lot of times you'll notice you'll have a little bit here, okay? So especially coming downhill, I'm going to come down, I'm going to hook, I let it build, down, hook, let it build, down, hook, let it build, okay? So usually what happens here, I'm concerned with right here, right here. Now let's look at the side profile from it, okay? When I do that, I'm going to bring my wire and my weld across here. So my weld's going to be here. Here's where I've seen a lot of issues when we've taken this technique and we've done destructive bend tests on it. Now you wouldn't necessarily see this on an x-ray, and we haven't, but some particular crane that I worked on, we had to x-ray it, my weld, and then we had the destructive bend test it both. So the destructive bend test was to make sure that we got good fusion. Lack of fusion can be very minute and very small to where it's hard to pick up sometimes with x-ray. So what happened here on this test is every one of these weld patterns, when I come around to right here, is I wasn't tying in to the bulk of this weld. So I'd come around here, and here was warm, but specifically, especially because my speed was faster, right here was where I would have a lack of fusion. It ended up being right at that spot right there. And you could tell it was at every ripple on my offside specifically, okay? So now what I do, if I know it's a critical weld versus a cosmetic weld, if I do, I had to change my technique up, they let me retest right away. So then what I do is I make sure that I umbrella it just like 60-10 downhill, so that my weld puddle is staying consistently this way, and my ramp looks more like this coming into it, okay? So I'm guaranteeing fusion along the base and the sides. Okay, let's go back to the chapter. Look. Turn that light back off. So here's a few different weld profiles, okay? Usually what I see is the far right, to where it's unacceptable, too low. I hardly ever see it too high on the left-hand side. It's usually on the bottom side by nature. Excuse me. Okay, travel and work gun angles. Okay, axis of the weld, this is a 2F weld horizontal. Weld axis lays here. Travel angle, work angle. All right, so my drag angle, normally I'm going to be dragging it with the exception of pushing vertical. So you might even see a question on the test that asks something about that, like is it typically a push or a drag? Almost always you drag, however, vertical up you may be pushing, right? And then it's, you know, sometimes I put questions in there just like that to see if you're paying attention. You know, I may even give you an extra point if you were to say, yes, typical, however, vertical up, you have to push the weld pattern up instead of dragging it, okay? So, travel angle versus work angle, okay? Feel free to read through this. Arc length is shortened, the arc voltage is reduced. As arc length is lengthened, arc voltage is increased. Trying to find it and push it further away. So remember, we're running a constant voltage welding machine. So it is constantly trying to maintain the voltage. Sometimes it usually does a good job, but I've put a multimeter on it and measured them, and I've seen up to a 1.5 volt difference. Same thing with shielded metal arc welding. So for example, the 6010 whip and pause, I've seen a 25 to 30 amp difference just on the whip and the pause alone. Okay, and remember, it doesn't always stay there. You have to be able to regulate it with wire. It's very minimal, maybe half to 3/4 of a volt usually is all you'll see, because you're not doing a drastic amount of like a whip and a pause. It's more just steady manipulation and about the same arc length, okay? Welder has the complete control of welding current and arc length by setting the wire feed speed on the wire feeder and voltage on the welding machine. Okay. So with that, let's see if it talks about it here now. Let's talk about voltage. Decided effect upon surface heating in a weld profile noted in bead height and bead width. Correct. However, for most machines, most wires will have a specified range. You can influence it, and remember, everybody's speed is a little bit different. So you want to set the machine to the correct weld bead and weld pattern and your natural speed, okay? Now if you're setting up a mechanically driven welding machine, that's a different story. However, most of us are doing this by hand. You know roughly what you can weld, wire speed wise and voltage wise, okay? Anytime you take it away, bring it in, it changes. So high arc voltages with short circuit transfer results in the globular transfer. Spatter's very prone, reduced deposition efficiency, okay? So if you start to see a lot of globular stuff, you want to make sure to back your arc voltage down. Excuse me. a lot of spatter, possibly drop your voltage down one setting, keep your wire speed the same, and try that, okay? Spray arc does have a hissing sound, sharp crackling sound with the proper arc voltage. We do some spray arc in here on welding 3 as well, okay? Okay, you can see here, the short circuiting is on the left hand side, spatter in the middle, spray. I'm not really sure what they're trying to get with this picture. I think it's a lot easier to see when you're out there. Okay, trying it. Okay, this is a pretty good example of just, you don't have to remember this formula by any means or anything else. But it just talks about, right here, we talk about the funnel, and the certain amount of penetration. I've talked to you about like the pressure washer effect. Think of the angle in the funnel of your arc, your electric arc. As it comes out, the further away you go, the wider it gets. Further in you are, closer you are. So you can see that it's not as wide. Here it's super wide. You got better deposition here, real flat, wide pattern here, so forth, okay? Less penetration as well on this portion, naturally, because you're spreading the heat out. Here the heat is more focused, okay? Penetration comparisons, as you can see there on the left, shallow. Here's arc voltage is too high for the travel speed. You start getting a lot of undercut. This is, when your wire speed's usually turned down low and your voltage is high. Not really the greatest profile. Here's what we're looking for. And then here as well, this is when your arc voltage is way too low and your travel speed is slow as well. You're getting a lot of excess weld. It's just laying on top, real high crown, and so forth. Okay, wire feed speed. Here's one of the biggest misconceptions in welding, okay? It says there's a fixed relationship between the rate of filler wire burn off and welding current. Okay. Electrode wire feed speed determines the welding current. The current set by wire feed speed control on the feeder. So excessive speed means the welding machine cannot put out enough current to melt wire fast enough. Okay? Decrease in speed results in less electrode being melted and possible burn backs. Generally, a high setting of filler wire speed rate results in short arc, slow speed, and long arc. Alright, so let's try to break down this whole thing real quick of what it's telling us. I want to read something from the book. Excuse me. Sorry, I'm yawning. It said the current is set by the wire feed speed control in the wire feeder. The welding machine supplies the amount of current amps necessary to melt the electrode at the rate required to maintain the preset voltage